Good morning everyone. Today my name is Karuthapandi. Today we discuss about basics of engineering thermodynamics. I am teaching from Assistant Professor, Pearson College of Engineering and Technology, Tirunelveli. What is thermodynamics? Thermodynamics, it is nothing but it is the study of heat in motion. Okay. Definition: thermodynamics is the study of energy and its transformation and the laws of governing these transformations. It deals with the interrelations of heat, work and energy. In our life, in our daily life today, we see so many heat transfer and heat flows in daily. We take a cup of tea and pour in the cup of tea and in the table. Okay, tea takes some time. After that, it automatically decreases its temperature. That is flow of heat. Okay, and take ice in a cube of ice and place the table. And after some time, it is melting. It is heat transfer. Okay. Scope of thermodynamics. In future and in current trend, analysis and optimization of new energy systems depends upon the thermodynamic systems, and innovation of new design of engines, power plants, refrigerators and HVAC, heating, ventilation and air conditioning systems. It is the basics of its design apart from the thermodynamic systems. And third one, understanding natural and industrial process. These are the scopes of thermodynamics. And its applications are aerospace engineering, chemical processes and renewable energy systems. Importance of thermodynamics. Why it is using in engineering? We design a new energy systems depends upon the thermodynamics, how it works and how it plays a vital role, what are the factors influencing a thermodynamic systems, how its heat transfer takes from one point to another point. What is the main factors? Consider that pressure, temperatures, energies, works. Okay, and how its energy losses introduced in industrial process, and how its sustainable and eco-friendly technologies. These are the importance in thermodynamics, and some examples are we introduced in that power generation using Rankine and Brayton cycles. Rankine cycles are used in power generation and Brayton cycles are used in jet propulsion systems and rocket propulsion systems. Each and everything should carry heat transfer, and thermodynamics plays a vital role. And internal combustion engines also carry a heat transfer, heat flow motions, thermodynamics it carries, and advanced cooling and heating systems of our buildings, air conditioner, HVAC. These systems are introduced by the thermodynamics, and these are the advanced techniques of thermodynamics. This system. What is system? System is nothing but it is in a specific region or quantity of matter being studied. Okay, first of all, for example, a glass of water, it's a system. The glass is a boundary. Except the boundary and the system is called surrounding. That means everything external to the systems. Okay, boundary is nothing but the physical or imaginary surface that separate the system from its surroundings, that is boundary. and further classified the systems: open system, closed system, isolated system. Open system means mass and energy exchange from system to surroundings or surroundings to systems. Okay, for example, turbine is an example for an open system. Closed system means only energy will exchange, not mass transfer. Okay, it's a piston cylinder engines, compressors. These are the example for closed system. Then isolated system, no exchange of mass or energy. Example, thermoflax. Thermoflax is a wonderful example for isolated system. It take a cup of tea or coffee or cool drinks. It takes some time to reduce its temperature, decrease the temperature. That is the isolated system. This figure shows the blue represents the systems, the dashed lines are represents the boundaries, and except the system's boundaries, surrounding is present. Okay, the system, surrounding and boundary, these are the universe. These three are combined with each other. It is called as universe. Shown here figure, a cup of tea. First one, open system, heat only transfer. The cup of tea is fully open with the surroundings. So the heat will transfer and the mass, the vapor is called as mass. These are transferred to the surrounding. The next figure shows the closed system. The cup of tea is closed by a lid. Only heat will transfer by the convection, no mass transfer. In first figure, the vapor is move around the surroundings, but this vapor is closed by the lid. Okay, no mass transfer is occupied in these systems. Then third one is thermoflask. This is isolated system. No, the flask cap is closed. No mass transfer, no heat transfer. It will take some time to reduce its temperature. These are the thermodynamic systems: state, properties, and processes. What is state? State is nothing but it describes where it is placed. What is the point? That is the state. Okay. Properties means it classified into intensive and extensive. Intensive properties depends upon the system size and shape. For example, temperature and pressure, density, color. These are the examples for intensive properties. It fully depends upon the system size and shape. Extensive property means depends on the system size. Example, volume, mass, weight. These are the extensive properties. Okay. In further, move to processes. Process is classified into isothermal, isobaric, isochoric, adiabatic, isentropic process. These are the categorized of processes. Process is from one point to another point. The heat flows depends upon this process. Okay. Isothermal means constant temperature. The temperature is a constant. Adiabatic means no heat transfer between the system and surroundings. Isobaric means constant pressure process between the system and surroundings. Isochoric process means constant volume, no changes in volume. The volume should be constant. Example, heating a piston cylinder assembly in a thermodynamic process. I will show in the next slide. First one, isobaric process. The vessel is opened by the lid. Okay, lid. The vessel is heated by a heat sources. Okay, the lid is open. After some time, the vapor will be move around the surrounding, move to the surrounding, but a pressure is constant. If the vessel is closed, the pressure will increase. So in some time the pressure will increase. Okay, but in isobaric process, the lid is open, so the pressure remains constant. The next one is isochoric process. In isochoric process, the thermodynamic process in which the volume remains constant is called isochoric process. In isochoric process, the volume remains constant. The vapor does not move away from the system to surroundings because the vessel lid is closed. Then next move to adiabatic process. Adiabatic process is nothing but no heat transfer between the system to surrounding or surrounding to system. In this for the adiabatic process, we have a insulated cylinder wall with the piston. Okay, the moving fluid is only static conditions, that is no heat transfer between system to surrounding to system. And finally, isothermal process. The isothermal process, the vessel is heated by a heat sources. Inside a thermometer on the fluid, the temperature is constant at everywhere at the vessel. Okay, the heat is constant, the temperature remains constant. This is known as isothermal process. Equilibrium, thermodynamic equilibrium. A system is in equilibrium when there are no net changes in this macroscopic properties over time. A thermodynamic equilibrium means which is equilibrium in thermal equilibrium, mechanical equilibrium, chemical equilibrium. Okay, these three are generally say upon thermodynamic equilibrium. Thermal equilibrium means uniform temperature throughout the system. Consider a classroom or anything in a room. Measure a temperature at any point of this room should be constant. If your room temperature is 35 degree at any place, it is constant. That is thermal equilibrium. Mechanical equilibrium means no pressure gradients in the system. The pressure entire classroom should be constant. Okay. Chemical equilibrium means take a water. It's full of a content of H2O. No net chemical reaction occurring in the system. This is the example. Okay, two systems are said to be in a thermodynamic equilibrium when they are in thermal, mechanical and chemical equilibrium. We contain a container containing water. It's at 25 degrees Celsius. Wherever we measure, it is 25 degrees Celsius. The surrounding temperature is 25 degrees Celsius, and also water temperature is 25 degrees Celsius. And the chemical compositions, wherever we take a measurement, the chemical composition is H2O. Okay, and also the outside and the inside pressures are same. These are the thermal, mechanical and chemical equilibrium. Energy in thermodynamics. Form of energy: kinetic energy, potential energy, internal energy. Kinetic energy is energy due to motion. Whether the molecules are in a movement, it is kinetic energy. Potential energy means energy due to position in a gravitational field, then it is called potential energy. Internal energy is a combination of kinetic, potential, chemical energy or chemical energies, the pressure energy. These energies are combination, it is called internal energy. The microscopic energy related to molecular motion and interactions. Then energy transfers. Energy is transfer depends upon the work and heat. Energy transfer by a force causing displacement is called work. And energy transfer due to a temperature difference is called heat. Okay, clearly understand, I think. The zeroth law of thermodynamics: if two systems are individually in thermal equilibrium with a third system, they are in thermal equilibrium with each other. Take a three systems A, B, C, or take a 2 cup of tea. One is cold coffee and another one is hot tea, hot coffee, either it may be, and a room. These three systems are: first A system is a room, B system is a hot coffee, and C system is a cold coffee. These temperatures are entirely different from each other. The room temperature is around 25 degrees Celsius. The cold coffee is 15 degrees Celsius, and hot coffee is hot coffee means 85 degrees Celsius nearly. And these three systems are at some time, it takes some time in rest. At a specific time, three systems should be equilibrium conditions. Thermal equilibrium condition. These three systems should carry same temperature, same measurement, equally 35 degrees Celsius, 35 degrees Celsius, 35 degrees Celsius. Okay. Implications: establish the concept of temperature, forms the basis for temperature measurement and thermometers. Example: two objects in contact with a thermometer eventually have the same temperature. This is the figure for zeroth law of thermodynamics: A system, B system, C system. If the A system is thermally equilibrium with B and C, automatically the B and C are equilibrium conditions. This is the zeroth law of thermodynamics. It is the prerequisite for a first law of thermodynamics. Okay. This is the base for a first law of thermodynamics. Already we know the first law of thermodynamics. First law means the energy can be created, not be destroyed, but one form of energy is converted into another form of energy. The energy balance equation for a first law del U means change in internal energy. Q means heat divided or rejected, a difference of work done by the system. Okay. Heating a gas in a closed container increases its internal energy. If we remove a heat, if add a heat, the internal energy should be changed. If they remove a heat, the internal energy should be changed. How the work will be done? Work done by the system or work given by the system, whatever it may be, the internal energy will be system. The heat added or heat removed, the internal energy will be changed. Application of the first law: closed system, energy transfer only in the form of heat and work. Example: a gas in a piston cylinder undergoing a compression. Okay, understand? Then open system, mass, heat and work can across the boundary. Example: a turbine where steam flows in and does work. The next slide: specific heat. Specific heat is nothing but it is categorized into specific heat at constant volume, specific heat at constant pressure. The specific heat at constant volume represented C suffix V. The specific heat at constant pressure is C suffix P. Specific heat at constant volume is nothing but heat required to raise the temperature of a unit mass at constant volume. Take a vessel and kept a water in this vessel. Heat add to the vessel. After some time, the temperature of a vessel and also a water should be raised. The temperature of a boiling water, the boiling point of a water is 100 degrees Celsius. Already we know that. After take some time, initially the water temperature is 25 degrees Celsius up to 100 degrees Celsius. Every temperature should be raised depends upon the constant volume or constant pressure. If we take a water in a open lid process, open lid container, it's a constant volume process. If constant pressure process, if a lid is closed, then it's a constant volume process. Specifically, at constant volume means heat required to raise the temperature of a unit mass at constant volume. The heat required to raise the temperature of a unit mass at constant pressure at specific heat at constant pressure. The relation for ideal gases means Cp minus Cv equal to R. The specific heat at constant to the difference of specific heat at constant volume, which is equal to the gas constant R. The second law of thermodynamics, the two scientists are classified the second law of thermodynamics. First one, Clausius statement. The Clausius said he cannot spontaneously flow from a colder to hotter body. Only the heat, volume, pressure, these are spontaneously flow from colder to hotter, spontaneously flow from hotter body to colder body. But the heat flow from colder body to hotter body, it needs a external sources, external aid to move a heat from colder body to hotter body. This is a Clausius statement. Kelvin-Planck statement means no engine can convert all the heat it absorbs into work. 100% of input does not provide 100% of output. Some losses will occur from the engines, pumps, whatever the thermodynamical systems. Okay, from losses, energy losses, pressure losses, some heat absorptions. Only 25 to 30% of work will be done by a system. That is the Kelvin-Planck statement. No engine can convert all the heat it absorbs into work. And furtherly, entropy. Entropy is nothing but the measure of disorder or randomness in the system. If we apply heat to the system, the molecules of particles or anything fluid, it will be move randomness or disorderness. How the fluid molecules are movement by the measure of randomness. Okay, that is called entropy. It is represented by del S, which is equal to Q reversible by T. Reversible process means the process will be reversible. Take a ice, for some time it will be rest, it will be melting. Okay, it will pour by a melting water and it will be freezing. Sometime it will make a ice. That is reversible process. Ice to liquid and liquid to ice. This is called reversible process. For example, the second law for thermodynamics, the process is spontaneous, occur on its own. So entropy of the universe is increases. The air leaks from, if we take a balloon, the hole, to make a hole, the air leaks from the balloon on its own, because the air contain a high pressure, the surrounding contain a low pressure. So the high pressure to low pressure is spontaneously occur. But in this case, the process is not spontaneous because does not occur on its own. So entropy of the universe is decreases. Air never enters the balloon on its own. We take external source to compress the air and induce the air to the balloon. The entropy statement of the second law of thermodynamics: in all spontaneous process, the entropy of the universe increases. Next, we measure the temperature, entropy, pressure, volume by the graphs or diagrams. TS diagram shows that temperature versus entropy. It's useful for analyzing efficiency, how the systems works efficiently or not. This is produced by the TS diagram, and the PV diagram, it shows the pressure versus volume. Visualize work done during a cycle, how the work done will make by the system or on the system. Okay, these are the TS diagram and PV diagrams. The definitions, by the definition of heat engines. Heat engine is nothing but automotive engines, heat engines, a device that converts heat into work. A fully heat converts into work, that is called heat engines, which efficiency is eta, which is equal to work done by heat added. Which is and another formula is 1 by cold body to the hot body. QH represents the heat input from the hot reservoir. QC is heat rejected to the cold reservoir. Example: steam engines and internal combustions. For example, for heat engines, once again repeat you, efficiency which is equal to 1 minus hot body of hot reservoir to cold reservoir to hot reservoir. Carnot cycle, it is a to idealize the cycle, it is it contains four process. The first one is isothermal expansion, second one is adiabatic expansion, third one is isothermal compression, fourth one is adiabatic compression. These four are to make a Carnot cycle. Idealized cycle, it is an imaginary cycle. Okay, static Carnot says 100% of engines work. How much 100% output will be produced by the Carnot cycle. In practical application, it is not possible now. Okay. This is PV diagram. This is TS diagram. See a PV diagram. First of all, isothermal expansion. Isothermal expansion means the temperature is constant at the expansion process. Okay. 1 to 2 is iso. First, before that, we see a figure. We take a cylinder piston arrangement in a sequential manner. First, the A figure shows we added a heat. Automatically, the fluids moves upward to rise the piston upward direction. That which means expansion, isothermal expansion. At the time, the expansion will take isothermally. The temperature will be constant, and furtherly added with some heat. The expansion will be adiabatic expansion. No heat transfer from system to surroundings and surrounding to system. It shows in the figure B. And okay, the process 1 to 2 is isothermal expansion, and 2 to 3 is adiabatic expansion. In further move to, and the heat is removed from the system and the piston is slowed down, reduce its volume from 3 to 4. Okay, that is isothermal compression. After some time, it fully compressed in a adiabatic manner. No heat transfer between system and surrounding in a figure D. The PV diagram shows that 3 to 4 is isothermal compression and it's furtherly moved to adiabatic compression 4 to 1. This is expressed by the PV diagram. Next, thermodynamic cycles. The power cycles means converted heat into work. Rankine cycle, Otto cycle, diesel cycle. Rankine cycle is only applicable for power plant, other than means power generations. Otto cycle means power produced by the petrol engine. Diesel cycle means power produced by the diesel engine. Refrigerant cycles, we remove heat from a cold body. For example, vapor compression system or vapor absorption system. These are used in refrigerant cycle. Example, air conditioning system and power plants. Ideal gases versus real gases. Ideal gases loss means PV, which is equal to nRT. Assumes no intermolecular forces and negligible volumes of particles. With that is called ideal gas law. Real gases means deviate from ideal behavior at high pressures and low temperatures. Described by the van der Waals equations. P plus A divided by V square, V minus V, which is equal to RT. That is the real gas van der Waals equations. It is derived by the van der Waals. Then heat transfer mechanisms. The heat transfer means already we know that the heat is transferred by a 5 mechanisms, majorly 3: conduction, convection, radiation, then further into boiling and melting. Okay, conduction means heat transfer through the solids by molecule interactions. If you take a solid particle, the movement of air, the movement of molecules through the solid, that is conduction. If a heat transfer in fluids by the motion of the fluid itself, convection. If the heat transfer takes place in a fluid particles to solid, otherwise solid to fluid, then it is called convection. Radiation means heat transfer by electromagnetic waves without a medium. If vacuum, it takes a by the vacuum only appear the heat transfer by a electromagnetic waves. The ultraviolet radiations, these are the by the radiations. Then Otto cycle. The Otto cycle is an idealized thermodynamic cycle that describes the functioning of a spark ignition internal combustion engines. The named after Nicholas Otto, the inventor of the first practical internal combustion engine, which means petrol engine, gasoline powered cars, motorcycles and small engines are based, it stands upon the Otto cycle. Key components of Otto cycle, these are the parts: pistons moves within the cylinder, the piston is in between the two cylinder walls, then cylinder, the chamber where the cylinder cycle occurs. The cycle means the Otto cycle. Spark plug ignites the air fuel mixture, crankshaft converts linear motion into rotational motion, fluid medium air. The air is compressed by the fuel and produce power. Status of the Otto cycle, already we know that forced choke, so intake, compression, power and exhaust. These are the replaced by the isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejections. Isentropic compression means no friction is placed here, no mass transfer is placed here. Adiabatic compression of the air fuel mixture. Constant volume heat addition means ignition and combustion at constant volume. We introducing a heat itself. Isentropic expansion means after the power stroke, adiabatic expansion will take place automatically. And constant volume heat rejection by the silencer or exhaust system, external exhaust valve, exhaust heat released at constant volume. These are the PV diagram and the TS diagram for Otto cycle. Initially the intake, the air intake from intake and it compressed from 1 to 2. Isentropic compression. In the isentropic compression, the piston will move BDC to DDC. At the same time, the compression, the pressure will rise. The volume should be decreased. and further 2 to 3 process means constant volume heat addition. In this process, by the spark plug we adding some heat to the cylinder, the pressure will have to be constant. By the process 2 to 3 the heat will added, but at the same time the pressure will constant. And after the power store, the isentropic expansion will take place. The piston moves from VDC to VDC spontaneously 3 to 4. At a time the work will generated. That means the piston moves from VDC to VDC. The output will be produced. At the same time the expansion will be placed. And 4 to 1, the expansion valve will be opened. The exhaust gas will be released from by the system. This is constant volume heat rejection. At V1 to V4. At the piston is placed at top dead center. The volume V2 equal to V3. The piston placed at bottom dead center. Okay. These are the explained by the figure. Point 1 compression will take place. Point 2 to 3 process 2 to 3 heat adding by the spark plug. Process 3 to 4 expansion will take place, and 4 to 1 heat rejection by the exhaust valve. And the next move to TS diagram displays temperature when the entropy changes. Okay, temperature versus entropy changes. First process 1 to 2 compression will take place. Process 2 to 3 entropy increases. Process 3 to 4 expansions. Process 4 to 1 entropy decreases. The description. The piston compresses the air fuel at process 1 isentropic compression. The piston compresses the air fuel mixture adiabatically. Adiabatic means no heat transfer is here, no heat exchange. That means Q equal to 0, present temperature automatically spontaneously increases. T2 which is equal to T1 V1 by V2, product of V1 by V2 by specific heat of minus 1. Then P2 which is equal to P1 of V1 by V2 into power of gamma, where gamma is nothing but this is specific heat ratios Cp by Cv, and the compression ratio V1 by V2 is the compression ratio of a cylinder. Then process 2 to 3 constant volume heat addition. The compression occurs at constant volume due to the spark plug. Heat is added to the system. The pressure and temperature rise significantly. The heat added is a heat which is equal to mass into specific heat at constant volume. The temperature difference of 2 to 3, where M is the mass of the gas. The process 3 to 4 is the isentropic expansion. High pressure gas pushes the piston outward performing work. Adiabatic process. Q which is equal to 0 and the temperature and pressure decreases. The equations are shown in T4 which is equal to 3 product of V3 by V4 and the gamma, the specific heat minus 1, and the exit pressure of which is equal to process at 3, pressure at 3, and the product of V3 by V4 and the specific heat. And the process to 4 to 1 constant volume and heat rejections. The piston reaches the end of the expansion stroke. The heat is rejected at constant volume. Q1 is greater than 0. The pressure and temperature will be dropped. These are the efficiency formula for the Otto cycle. Efficiency formula is one difference of Q out by P in, output by input, and the compression ratio is 1 minus 1 by the compression ratio of gamma minus 1. Okay. Then real Otto cycle is ideal Otto cycle. In ideal cycle assumption, the perfect gas behavior is placed here, no friction or heat losses. But in between the piston and cylinder, the friction will be placed in a real cycle. But ideal cycle cases, no friction is placed here. And in combustion in a real cycle, non-instantaneous combustion process will take place here. The combustion will take place by the spark plug. Application of the Otto cycle means gasoline engines, cars and bikes, power tools, chainsaws and portable generators. Advantages: high power to weight ratio, quick response to load changes. Then limitation of the Otto cycle. Practical challenges are lower efficiency compared to diesel engines. Further we move to diesel engines. Limited by knocking and detonation risk at a high compression ratio. At a high compression ratio, the sound will be occurred by the knocking and detonations. Internal impact, emissions of carbon dioxide and nitrate oxides and unburned hydrocarbons are emitted by the Otto cycles. Innovation and future trends are advanced fuel engine system to improve combustion efficiency. Then hybrid engines are combined Otto cycle engines with electric motor for better fuel economy. For better fuel consumption, to combine the Otto cycle engines with an electric motor. Furtherly, alternative fuels are used to biofuels, hydrogens and synthetic fuels are used to Otto cycles to produce best efficiency to make best cars, automotive vehicles. The Otto cycle is the foundation of spark ignition engines, SI, that means SI engines. Understanding the cycle helps improve engine performance and efficiency. That the procedures of the Otto cycles, innovation materials, fuels and engines designs are encouraging the relevance of the Otto cycle in modern energy systems. Then further move to diesel cycles. Diesel cycle means the diesel is an idealized thermodynamic cycle describing the functioning of a compressor engine system, IC engines, named after the Rudolf Diesel, the inventor of the diesel engines. The application means where the high torque is needed, the trucks, buses, locomotives, ships and heavy duty equipment are only working by the diesel cycles. The key features of the diesel cycles are fuel ignitions, the self ignition due to high temperature from compression, no spark plug is needed, compression ratio higher than the Otto cycle, typically ranging from 14:1 to 22:1. The fuel efficiency is higher than gas engine, that means Otto cycle, due to greater thermodynamic efficiency. Process in the diesel cycle, these are similar to the Otto cycle, but only one thing, the pressure heat addition, the constant volume heat addition. Okay, these are the constant pressure, the constant volume. These are the two different things compared to the Otto cycle. Isentropic compression is similar, same. Isentropic expansion is same. Isentropic compressions means the adiabatic compression of air is drawn to the cylinder. The constant heat addition takes place by the automation of fuel at a constant pressure at a drawn the air. Then it is automatically combustion will take places. Isentropic expansion is after the combustion the cylinder moves DDC to BDC automatically. Constant volume heat rejection, when the exhaust valve is opened, heat is rejected at a constant volume process. In a PV diagram, the first two, process 1 to 2 is compression, 2 to 3 is heat addition, process 3 to 4 is expansion, and 4 to 1 is heat rejection. By the GS diagram, displays temperature and entropy changes. Process 1 to 2 is compression, 2 to 3 is entropy increases, 3 to 4 is expansion, 4 to 1 is entropy decreases. And this is isentropic compression for process 1 to 2 is isentropic compression, 2 to 3 is constant pressure, because the P2 which is equal to P3, constant pressure heat is addition in this process, and the process 3 to 1 and 4 is isentropic expansion. In this process the piston is moves from DDC to BDC automatically. Then by this process is called as power stroke. This stroke is called as power stroke, and 4 to 1 is constant volume heat rejection. Okay. The process 1, the piston compresses air adiabatically raising its temperature and process, no heat exchanger, that means Q is equal to 0. Process 2 to 3 is constant pressure heat addition, fuel is injection into the compressed air and combustion occurs. Heat is added at constant pressure, Q in greater than 0, and also volume increases as the piston moves outward. In this process, heat is added means mass of gases into specific heat at constant pressure, then into temperature difference. Process 3 to 4 means isentropic expansions, combustion gases expanded adiabatically, performing work on the piston. Note heat exchange here, temperature and pressure decreases. Then process 4 to 1 is constant volume heat rejection. The piston reaches the end of the expansion stroke, heat is rejected to the surroundings at constant volume, Q are greater than 0, and pressure and temperature drop. The efficiency formula is similar to the Otto cycle. Efficiency, the heat which is equal to 1 minus output by input, and the compression ratio is V1 by V2, and the cutoff ratio is V3 by V2, and the specific heat ratio is Cp by Cv. The advantage of the diesel cycle means higher efficiency due to higher combustion ratio, better fuel economy and durability. The disadvantages of slower acceleration response, heavier and more expensive engines. The applications of the diesel engine vehicle means diesel cycle, heavy vehicles, trucks, buses, trains, marine engines, ships and submarine, industrial equipment, generators and construction machinery. Practical challenges are larger and heavier engines compared to gasoline engines, emission to particulate matter and nitrogen oxide (NOx). Environment concerns require advanced emission control systems. The innovation and future trends are currently using the COBA injection systems and hybrid diesel engines, combined diesel with electric power for petrol fuel economy, alternative fuel uses of biodiesel, synthetic diesel and hydrogen. The diesel cycle is fundamental to high power and efficient engines. Its higher efficiency and torque make it ideal for heavy duty applications. The closing up of the diesel cycle, innovation and environment regulations continue to shape the future of diesel engine. These are the full of basic engineering thermodynamics. Thank you.